There is a particular kind of silence that lives in the forests of central India just before the sun disappears. Not the silence of emptiness, the silence of things waiting to be noticed. The trees hold still. The air thickens with something older than language. And beneath the soil, beneath the roots and the red earth and the compressed weight of centuries, something glimmers. Not gold, not a buried artifact with a label attached to it, something far stranger. A liquid metal that refuses to freeze, refuses to rust, refuses to behave like anything else the natural world has produced. Something that ancient civilizations across the globe looked at and immediately understood. This is not ordinary. We are told that mercury is a hazard, a toxin, a thing to be contained, regulated, disposed of carefully. The warning labels are everywhere. The restrictions multiply every decade. And yet, if you go back far enough, back past the industrial age, past the medieval alchemists, past even the earliest Greek physicians, you find that mercury was not feared. It was sought. It was mined at enormous human cost, refined with extraordinary technical precision, and used in ways that modern science is only now beginning to revisit. Something changed between then and now. The question is what? The soil of the Indian subcontinent holds a secret that geological surveys have confirmed, but historians have largely refused to discuss. There are concentrations of mercury in this landscape, specific, localized, unusually dense concentrations, in places where no natural geological process can convincingly explain their presence. The formations don't follow the patterns of natural cinnabar deposits. They cluster near the ruins of ancient structures. They appear at depths consistent with deliberate burial or processing residue. And when archaeologists have noted them, which, to their credit, some have, the findings have a curious way of disappearing into archives and staying there. This is not a story about conspiracy, though it will brush against that idea. It is not a story about ancient aliens or mystical powers, or the kind of breathless speculation that makes serious historians wince. It is something more uncomfortable than that. It is a story about evidence, real, physical, textual, geological evidence, that has been sitting in plain sight for decades, waiting for someone to stop looking past it. Ancient Indian texts describe mercury not as a curiosity, but as a fundamental material of civilization. They describe its properties with a precision that reads, to modern chemists, not as poetry, but as procedure. They describe its uses in medicine, in metallurgy, in spiritual ritual, and in something else. Something that the texts circle around with a specificity that is difficult to dismiss as metaphor. They describe machines, vehicles, objects that move through the sky. Consider what it takes to write about something with technical detail. You don't describe a fictional machine's power source, its materials, its maintenance requirements, and its operational limitations, unless you have some experiential basis for those details. You don't write occupational safety guidelines for a substance you've never actually handled. The ancient Indian writers who described mercury-powered flight were not imagining, they were documenting. Whether what they documented still waits beneath the Indian forest floor, whether the proof is still there, sealed in chambers and tunnels that no modern machine dug, is the question that will carry us through everything that follows. Somewhere beneath those trees, something glimmers. The only honest thing to do is follow the light. Every civilization that ever mined mercury left a mark. The Spanish mines at Almaden operated for more than 2,000 years and are now a UNESCO World Heritage Site. Their history celebrated, their records preserved, their significance embedded in the global narrative of ancient industry. The Peruvian mines at Huancavelica, worked by Incan laborers centuries before Spanish colonizers arrived, are documented as one of the most significant mercury sources in pre-Columbian history. The ancient Chinese use of cinnabar, the red ore that yields mercury when heated, is well recorded in texts spanning 3,000 years. These civilizations are on the map. Their mercury histories are known. India is not on that map, and it should be. The Deccan Plateau, the red-soiled interior of Rajasthan, the river valleys of Madhya Pradesh. These regions contain geological formations that specialists in mercury geochemistry have described as anomalous. Cinnabar fragments have appeared in excavation layers dating back 4,000 years and beyond. Soil samples taken near the ruins of pre-Indus Valley structures have returned mercury concentrations that, in any other context, would trigger immediate archaeological investigation. In the Indian context, they have tended to generate a footnote, a brief mention in a regional survey, and then silence. The Indus Valley Civilization, which flourished along the northwestern plains of the subcontinent between roughly 1300 and 1300 BCE, was one of the most sophisticated urban cultures in the ancient world. Its cities were planned with geometric precision. Its drainage systems were more advanced than anything in contemporary Europe. Its trade network stretched from Mesopotamia to Central Asia, and its artisans worked with materials. Specific copper alloys, distinctive ceramic glazes, peculiar chemical compounds that suggest a knowledge of material science far exceeding what the civilization is typically credited with in popular history. Among the materials found in Indus Valley contexts, cinnabar, red, crystalline, unmistakably present. The Sanskrit texts that followed the Indus era are even more explicit. The word they use is parada, mercury, and it appears not as an occasional curiosity, but as a recurring, central material in texts covering medicine, metallurgy, spiritual practice, and, most intriguingly, mechanical construction. The Rasaratna Samakaya, the Rasanava, the Charaka Samhita, these are not fringe documents. They are the foundational texts of ancient Indian chemistry and medicine, and they discuss mercury with the systematic detail of people who had regular, large access to it. You don't develop an elaborate multi-stage purification system for a substance you encounter once in a generation. You develop it because you need it, often in quantity and for purposes serious enough to justify the effort. The comparison with Almaden and Huancavelica is not decorative. Those sites are famous because historians recognized what the evidence was telling them. The evidence in the Indian subcontinent tells the same kind of story. Large-scale extraction, sophisticated processing, state-level organization. But the recognition has not followed. Whether that gap reflects oversight, assumption, or something more deliberate is a question worth asking carefully. What the geological and textual evidence together suggest is straightforward. Ancient India was not simply aware of mercury. It was, at certain periods, dependent on it, and the reasons for that dependence reach further than medicine or ritual. They reach upward, toward a technology so unfamiliar by modern assumptions that the researchers who get close to it tend to find their work quietly set aside. The underground of India remembers things that the official record has forgotten. The task is to listen. In 1904, a British geological surveyor working in the temple districts of South India broke the sealed stone chamber of a structure that local records dated to at least the 8th century CE, with architectural features suggesting construction on much older foundations. What he found inside was not what he expected. The chamber had been deliberately sealed, the stone fitted with a precision that spoke of intention, not accident, and within it, coating the inner walls in a thin, unmistakable film, was mercury residue, not rust, not mineral deposit, mercury, pure, processed, deliberately placed. He filed a report, it was archived, nobody followed up. That detail, so small, so quiet, so easily absorbed into the enormous administrative machinery of the colonial period, contains within it the entire shape of what this story is about. Not a single dramatic suppression. Not a vault of stolen documents, or a shadowy committee making decisions in a darkened room. Just a report, filed, forgotten, and left to sit in a colonial archive, while the question it contained aged without an answer. This documentary is the follow-up that never came. What we are building here, section by section and chapter by chapter, is a case, not a legal case, not a political one, an evidentiary one. We will move from the ground, the geological and archaeological record of mercury extraction in ancient India, to the texts, where the purpose of that extraction is described with a technical specificity that demands serious engagement. We will pass through the workshops and the manuscripts, through the engineers who looked at ancient descriptions and found real physics inside them, and through the colonial-era scholars who looked at the same material and found ways not to see it. We will arrive, finally, at the present, where experiments are being quietly conducted, where LiDAR imaging is revealing underground structures that weren't supposed to exist, and where the question of who is served by keeping this story marginal is more relevant than ever. The concept of suppressed history has been cheapened by overuse. It has been attached to theories that don't deserve it, used to lend drama to claims that evidence doesn't support. That cheapening has done real damage, because it has made it easier to dismiss questions that deserve to be asked seriously. The story of ancient Indian mercury technology is not cheapened by that association. It survives contact with scrutiny. It actually gets more interesting the closer you look. 3 questions will anchor everything that follows. First, who built the mercury extraction systems that the archaeological and geological evidence suggests existed beneath the Indian subcontinent? Second, why did they need mercury in quantities large enough to require state-organized industrial infrastructure? And third, what were they building? What was the end purpose of all that extraction, all that refinement, all that human cost that required a liquid metal as its operational heart? These are not rhetorical questions. They have partial answers drawn from texts and ruins and soil samples and archived colonial reports and partially declassified military documents. The partial answers are, by themselves, extraordinary. The full picture, what it would mean if the evidence holds together under serious investigation, is the kind of thing that changes not just how we understand ancient India, but how we understand the entire arc of human technical achievement. The forest is still there, the red soil is still there, and somewhere beneath it, the glimmer remains. Let us begin at the beginning, with the ground itself, and what it holds. There is a particular quality to an archaeological site that has been misread. Not destroyed, not looted, misread. The physical evidence is present, the artifacts are catalogued, the reports are filed. But somewhere in the process of interpretation, a decision was made, conscious or not, to fit the evidence into an existing story rather than let it tell its own. When you go back to those sites with fresh eyes and the right questions, what you find is not absence of evidence. It is evidence that was never properly asked about. The Edical caves of Kerala are primarily for their petroglyphs, ancient carvings etched into rock walls that archaeologists date to at least 6000 BCE. They are a tourist destination now, carefully protected, the carvings studied and photographed. But the caves extend deeper than the tourist sections. In the deeper chambers, where the carvings thin out and the rock closes in, survey teams working in the 1990s documented something that was mentioned in their technical reports and then effectively ignored. High concentrations of mercury in the sediment layers, clustered around what appeared to be deliberate stone hearth structures. The hearths were attributed to ritual fire use. The mercury was attributed to natural mineralization. Neither attribution has ever been formally tested. Move east across the subcontinent to the Vidarbha region of Maharashtra, where excavations of early Iron Age sites, some dated to around 1000 BCE, have produced clay vessels of a specific and unusual type. These vessels are double-walled, with a narrow neck and a collection channel built into the base. To a contemporary ceramics archaeologist, they are classified as storage containers. To someone familiar with historical mercury distillation technology, they are retorts, the specific vessel design used to capture mercury vapor and condense it back into liquid form during the smelting of cinnabar ore. The design is not common, it is not intuitive. It requires a prior understanding of how mercury vapor behaves when heated, how it cools, and how to capture it before it escapes into the air. The ancient Indian potters who made these vessels knew something about mercury's behavior that they had learned, specifically from working with it. Further north, in the ruins near Taxila, the ancient university city of the Gandhara region in what is now northwestern Pakistan, British archaeologists excavating in the early 20th century found thermal scarring on stone walls in specific repeating patterns. This scarring is consistent with the kind of localized, sustained high-temperature processing that mercury extraction requires. The official reports classified these structures as iron smelting facilities. Iron smelting and mercury extraction do share some infrastructure. Both require high-temperature furnaces, but the specific configuration of ventilation channels in the Taxila structures and the presence of bright red cinnabar staining on adjacent stone surfaces suggests a process distinct from iron work. Cinnabar staining is diagnostic. It is the unmistakable signature of a site where mercury ore was heated and processed. It does not appear accidentally. What these sites have in common is not just the physical evidence of mercury processing. What they share is the interpretive gap. the space between what the evidence shows and what the official record says. Each site has been documented by credentialed archaeologists. Each site's reports exist in accessible archives. The question of mercury extraction was noted, in passing, in each case. And in each case, that note was followed by silence. The clay vessels from Vidarbha become remarkable when you place them alongside a passage in the Rasanava, a Sanskrit text on mercury chemistry that scholars date to roughly the 10th century CE, but which claims to preserve much older procedural knowledge. The passage describes in specific terms the construction of vessels for mercury purification. The described design, double-walled, narrow-necked, with a base collection channel, matches the Vidarbha artifacts so precisely that the comparison, when first made by a researcher in a 2003 regional archaeology journal, prompted exactly the response that such comparisons tend to prompt in institutional settings. Silence, not refutation. Silence. The article was never cited. The comparison was never formally addressed. The ground speaks. The question is whether anyone is listening. When a modern organic chemist sits down with a translation of the Rasaratna Samukkaya, a Sanskrit text on mercury and mineral chemistry compiled around the 13th century, but drawing on much older sources, something unexpected happens. The chemical procedures described in its pages are not primitive. They are not poetic metaphors dressed in the language of transformation. They are accurate. The stages of mercury purification described in the text correspond, step by step, to processes that European chemistry would not formally document until the 16th and 17th centuries. The described reactions between mercury and sulfur produce compounds, specifically mercuric sulfide in its various forms, that match what modern chemistry confirms would result from those procedures. The text is not imagining what might happen. It is recording what does. Rasayana, the ancient Indian science of which mercury chemistry formed the central pillar, is typically translated as something like the way of essence, or, more loosely, the path of rejuvenation. In popular Western treatments, it gets folded into the category of alchemy, mystical, pre-scientific, concerned with the transmutation of metals and the pursuit of immortality. That framing is not entirely wrong, but it is deeply incomplete. Within the Rasayana texts, embedded among the spiritual and medical content, is a body of procedural chemistry that is systematic, reproducible, and grounded in observable physical reality. The ancient Indian chemists were not guessing. They were testing, recording results, and building on previous work with the same iterative logic that defines modern scientific method. Consider what the texts describe in relation to mercury purification alone. There are 18 distinct stages of purification outlined in the most detailed sources, each with specific reagents, temperatures, and expected outcomes. The stages are not arbitrary. They progressively remove specific impurities. First the organic compounds, then the sulfur compounds, then the metallic contaminants, until what remains is mercury of extraordinary purity. This level of procedural specificity, 18 precisely ordered stages, each with defined chemical purpose, does not emerge from casual experimentation. It emerges from generations of systematic practice, careful observation, and the kind of institutional knowledge transmission that requires large-scale, organized engagement with the material. You do not develop an 18-stage purification protocol for a substance you handle occasionally. You develop it because the substance needs to be exceptionally pure for its intended application. And the intended application matters here enormously. The Rasanava contains a passage that most of its scholarly translators have treated as metaphorical. The passage describes mercury that has been purified through all 18 stages as being capable, when set into circular motion within an appropriate vessel, of generating a force that moves against the stillness of the air. The translators have read this as spiritual language, a metaphor for the circulation of vital energy, the kind of imagery common in tantric and alchemical writing. That reading is comfortable. It keeps the text in its expected category, but consider it differently. Consider it as a technical note from a researcher who had observed something real, who had set purified mercury into circular motion in a sealed vessel, and measured something unexpected happening in the surrounding air, and who was describing that observation in the vocabulary available to them, the force that moves against the stillness, not a metaphor for spiritual energy, a description of thrust. The ancient Indian chemists who wrote these texts were not primitive. They were not naive. They were, by the evidence of their own detailed, accurate, chemically verified procedures, among the most sophisticated material scientists of the ancient world. When they described Mercury doing something extraordinary, the default assumption should not be that they were speaking metaphorically. The default assumption, earned by the accuracy of everything else they wrote, should be that they were speaking from experience. There is a text at the center of this entire story that most people have heard of, and almost nobody has actually read. The Vimana Shastra, loosely translated as the science of aeronautics, is one of the most controversial documents in the history of ancient studies. Its defenders describe it as a genuine ancient technical manual preserved through oral tradition. Its critics note that its written form appeared only in the early 20th century, when a scholar named Pandit Subbaraya Shastri claimed to have received it through a form of psychic channeling from an ancient sage. That origin story has done enormous damage to the text's credibility, and not entirely without reason. But the origin story and the content are two separate questions, and conflating them has caused serious researchers to dismiss material that deserves far more careful attention. What the Vimana Shastra actually contains, when you move past the controversy of its transmission, is a series of remarkably specific technical descriptions. It describes multiple types of flying vehicles, different designs for different purposes, different altitudes, different operational requirements. It describes their materials in terms that are identifiable, specific metal alloys whose compositions are described with enough precision to suggest real metallurgical knowledge, not vague mystical reference. And it describes, in one particular chapter, a propulsion system. The propulsion description centers on mercury, specifically on mercury heated in an iron container and set into controlled rotational motion. The heat causes the mercury to expand. The rotation creates a centrifugal pressure differential within the sealed vessel. The differential is directed through a narrow nozzle. The result, according to the text, is a sustained directional force sufficient to lift and propel a vehicle through the air. Now consider a patent filed in the United States in 1960 by an aerospace engineer working entirely within the modern tradition, drawing on contemporary fluid dynamics and electromagnetic theory. The engineer's name was Henry Wentworth Sherburne. His patent described a propulsion concept based on the rotational dynamics of a dense conductive fluid, specifically mercury, in a sealed container subjected to heat and electromagnetic field interaction. The resulting pressure differential, directed through a nozzle, would produce thrust. Sherburne had not read the Vimana Shastra. He almost certainly had never encountered it. He arrived at his design through the standard processes of modern engineering, beginning with known physics and working forward to an application. The convergence is not proof. It is important to say that clearly. Two independent people arriving at a similar concept through different routes does not confirm that either concept works, and it does not confirm the ancient Indian text's claimed age. But it does something significant. It establishes that the principle described in the ancient text is not the product of naive imagination. It is a real physical concept, one sophisticated enough that a trained aerospace engineer, working from first principles, arrived at independently. The ancient author of the Vimana Shastra's propulsion chapter was not fantasizing. They were describing a mechanism rooted in real physics. What they were describing, if their text preserved any trace of genuine ancient practice, was a civilization that had taken that physical principle and built something with it, something that flew, something that required as its operational heart large quantities of highly purified mercury, something whose construction would have demanded industrial-scale extraction infrastructure, specialized metallurgical workshops, and a state apparatus organized around the production and supply of a single, extraordinary liquid metal. The mercury concentrations in the Indian soil, the ancient processing sites with their misidentified retort vessels, the 18-stage purification protocols in the chemistry texts, the passage about the force that moves against the stillness of the air, a 1960 aerospace patent that arrived at the same principle from the opposite direction. The whisper is becoming difficult to ignore. There is a tendency, when encountering references to flying vehicles in ancient texts, to reach immediately for one of two explanations. Either the writers were speaking metaphorically, their sky chariots symbols of divine power, not descriptions of real technology, or they were imagining their accounts of aerial travel, the product of human longing for the freedom of birds. Both explanations are comfortable. Both allow the modern reader to absorb the ancient account without disrupting their assumptions about what the ancient world could do. And both explanations begin to fail badly when you actually sit with the volume and specificity of what the texts contain. The Ramayana describes the Pushpaka Vimana, the aerial vehicle that carries Rama, Sita and Lakshmana from Lanka back to Ayodhya. Not as a magical conveyance, but as a constructed object with a specific history of ownership, a described physical appearance, and operational characteristics mentioned in passing with the ease of a writer who assumes their audience knows what an aerial vehicle is. The vehicle has a sound, it casts a shadow, it moves at a speed that is described in relation to the wind. These are not the details of pure symbol. A symbol doesn't need aerodynamic specifics. The Mahabharata goes further. Across its enormous length, Vimanas appear more than 40 times, not always as central plot elements, but as background details, mentioned the way a modern writer might mention a car or a ship. They carry characters between locations. They are damaged in battles and require repair. They are described as being of different types, with different capabilities. One passage notes that a particular Vimana moved faster than mind, a poetic touch, but follows that immediately with practical observations about its shadow falling over enemy formations and its sound preceding it at a great distance. The poetry is there, but so is the engineering intuition. The Rig Veda, older than both epics, older than any continuous text tradition in the Western world, contains references to the Ashvins, divine physicians, who travel in a three-wheeled vehicle that moves through sky, land, and water. Three-wheeled. That specific detail appears in a context that, if taken as literal description, suggests a vehicle designed for multi-environment operation. A design principle that modern aerospace engineering arrived at only in the 20th century with the development of amphibious aircraft and hovercrafts. The Rig Veda was composed somewhere between 1500 and 1200 BCE. The multi-environment vehicle concept is either an extraordinary coincidence or something more unsettling. The Puranic texts, the encyclopedic compilations of ancient Indian knowledge, cosmology and history, describe Vimanas of multiple distinct types. The Samarangana Sutradhara, an 11th century text attributed to the Paramara king Bhoja, devotes an entire chapter to the construction and operation of flying vehicles. It describes 5 types of Vimanas, each with different materials, different propulsion methods, and different operational ranges. One type, the Tripura Vimana, is described as capable of operating in 3 domains: air, water, and space. Its structural requirements are listed. Its maintenance protocols are described. Its limitations are acknowledged. Limitations. That is the detail that carries the most weight. Mythology does not typically include engineering failure modes. Mythology gives its vehicles unlimited power and flawless performance, because the point is the symbolism, not the engineering. But the Vimana texts give their vehicles failure conditions. There are passages describing what happens when the propulsion system overheats. There are notes about which atmospheric conditions are dangerous for certain vehicle types. There are warnings about operating certain Vimanas at improper altitudes. These are not the details of divine fantasy. These are the details of real operational experience, preserved in a form that has survived thousands of years of copying and commentary, because it was worth preserving. The literature of the sky is enormous, ancient, consistent, and specific. It demands a better explanation than metaphor. The most important thing about the 1974 study conducted at the Indian Institute of Science in Bangalore is not its conclusion. The conclusion, that the Vaimanika Shastra's aircraft designs as literally described would not fly, has been quoted extensively by skeptics seeking to dismiss the text entirely. What receives far less attention is what the research team actually said in the full report, particularly in the sections that follow that initial conclusion. Because the engineers did not simply close the book, they kept reading. And what they found in the technical principles underlying those designs is where the real story begins. The team, led by aeronautical engineer H.S. Mukunda, examined the Vimana Shastra's aircraft designs using modern aerodynamic analysis. The conclusion about literal flight capability is accurate. The described shapes, as drawn by T.K. Elappa in the 1920s based on Shastri's descriptions, would not generate sufficient lift in their depicted form. But the report also noted something that its popularizers consistently omit: the underlying aerodynamic concepts embedded in the descriptions, the specific curvature relationships, the multi-chamber pressure logic, the references to gyroscopic stability mechanisms, were, in the report's own language, not obtainable by a person not well versed in the basic principles of aeronautics. That phrase is doing enormous work. It means that whoever wrote those descriptions had genuine technical knowledge of aerodynamic principles that were not independently developed in the Western tradition until the 20th century. The distinction matters profoundly. A fake document, invented in the early 20th century to deceive, would contain aeronautical concepts available in the early 20th century, and nothing more. What the IISC team found was aeronautical thinking that went, in certain specific respects, beyond what the supposed inventor could have known to fake. The gyroscopic stabilization references in particular drew the engineer's attention. The text describes a counter-rotating mechanism within the vehicle body that would function to stabilize the craft against rotational drift, a principle that was not formally applied in aircraft design until the development of advanced gyroscopic stabilizers in the 1950s. This is either an extraordinary coincidence, or the text preserves knowledge from a tradition that had actual flight experience to draw on. Dr. V. Raghavan, one of the 20th century's foremost Sanskrit scholars, spent decades examining the Vimana literature not as a believer in ancient technology, but as a linguist trying to understand what the texts were actually saying beneath their layers of translation and commentary. What he found was a consistency of technical vocabulary across texts separated by centuries and authorial traditions that suggested to him a shared inherited knowledge base rather than independent mythological invention. The same specific terms appear in the Ramayana, the Mahabharata, the Samarangana Sutradhara Hara, and the Vaimanika Shastra with consistent technical meaning. Not the floating consistency of shared metaphor, but the precise consistency of shared technical nomenclature. When the same word for a specific component appears in texts from 5 different centuries with the same contextual meaning, you are looking at a technical tradition, not a mythology. The Italian archaeologist Lucio Bernabo Brea, working primarily in the Aegean region, noted in a 1962 study something that has been largely unremarked upon in subsequent scholarship. The structural descriptions of certain Indian Vimana types bear striking formal similarity to descriptions of mechanical flying devices in ancient Greek and Roman texts, specifically in sources drawing on Alexandrian engineering tradition. The similarity is not in the mystical framing. The Greek and Roman accounts are thoroughly embedded in their own divine mythology, but in the specific engineering details, the reference to internal rotating mechanisms, to heat as a propulsive force, to the importance of vessel geometry in determining directional force. Either these traditions shared a common ancestor, or they arrived independently at the same engineering intuitions. Both possibilities are remarkable. What the engineers found when they read the ancient texts carefully was not confirmation of mythological fantasy. It was evidence of technical knowledge that should not, by the conventional account of history, have existed when it did. That finding has not been refuted. It has simply been set aside, waiting for the day when the questions it raises become impossible to avoid. The most technically specific passage in the Vaimanika Shastra comes in a chapter dealing with propulsion. The Sanskrit term used for this mechanism is shatyudgama, literally, the emergence of force. And the description that follows is not vague. It is not poetic. It is, in its precise details, something very close to a technical specification. The mechanism begins with an iron vessel. The choice of iron is not incidental. Of all the common metals available in the ancient world, iron is among the most resistant to mercury's corrosive properties. The vessel is sealed with a single directional port. Inside the vessel, mercury, described specifically as mercury that has undergone the full purification process, not raw cinnabar extract, is placed in a quantity calibrated to the vessel's interior volume. The vessel is then subjected to external heat. As the mercury heats, it is set into rotational motion by a mechanism the text describes obliquely, but which appears to reference a spinning internal structure, possibly a disk or ring. The combined effect of heat-induced expansion and rotational centrifugal force creates what the text calls a vega, a directed force, that emerges through the directional port and provides sustained movement. Let us translate this out of the ancient vocabulary. A sealed iron chamber, mercury under heat, forced rotation, directional exhaust. This is, in its basic configuration, a description of a reaction propulsion system using mercury as its working fluid. The heat provides energy input. The rotation converts that energy into directional pressure. The exhaust port directs the resulting force. The physics are real. None of this requires the suspension of any law of thermodynamics or fluid mechanics. What makes this passage remarkable is not just that it describes something that could work in principle. It is that NASA, working entirely from modern physics in the 1960s, arrived at a nearly identical conceptual design. The mercury vortex engine concept explored by aerospace researchers in the mid-20th century used heated, rotating mercury in a sealed chamber to generate propulsion. The specific parameters were different. Modern engineering brings precision that the ancient text lacks, but the operational logic was the same. Mercury, heat, rotation, directed force. The concept was explored, found theoretically promising, and eventually set aside not because the physics failed, but because the engineering challenges of handling mercury safely in a spacecraft environment proved prohibitive with the materials available at the time. That last detail deserves careful attention. The reason NASA's mercury propulsion research stalled was not that the physics was wrong. It was that making it work safely and practically was too difficult given contemporary engineering constraints. The ancient Indian texts, in contrast, describe the mechanism as a solved engineering problem, something that has been built, tested, refined, and documented. If the physics is sound and the engineering challenge is real, then the ancient account isn't describing a fantasy. It is describing a solution to an engineering problem that modern technology has not yet solved. The solution may be incomplete, the records may be fragmentary, but the direction they point is unambiguous. The word Shaktyudgama, the emergence of force, appears in the Vimana Shastra, and then, in different language but identical concept, it reappears in a 1960 American aerospace patent, and then again in classified military research documents, and then in small laboratory experiments reported in journals that few people read. The emergence of force, the same emergence, the same force, traced across thousands of years of independent discovery, always arriving at the same place. Mercury, heat, rotation, and something extraordinary happening in the air. The texts are not mythology. They are notes from a laboratory that no longer exists. The question of where that laboratory was, who ran it, and what happened to it, carries us directly into the oldest layers of the investigation. Every great body of technical knowledge has a history. Mathematics in ancient India traces its lineage from the Sulba Sutras through Aryabhata and Brahmagupta in an unbroken chain, each mathematician building explicitly on the work of predecessors, citing them by name, correcting their errors, extending their methods. Astronomy follows the same pattern. Ayurvedic medicine follows the same pattern. The lineage is traceable, the evolution is visible, and the resulting confidence in the historical reality of that knowledge is entirely justified. For the Vimana technology described in the ancient texts, the lineage does not work this way. When the Vimana Shastra attributes its knowledge to the sage Bharadwaja, and when the Samarangana Sutradhara traces its aerial vehicle descriptions to still older sources, and when the Ramayana's authors describe the Pushpaka Vimana as having been constructed in an era long before the narrative present of the poem, what they are consistently doing is pointing backward toward an origin they cannot reach. The knowledge exists in the texts, but its source lies beyond the horizon of recorded history. It claims to be a copy, not of a recent text, of something very old. There are two ways to interpret this pattern, and both deserve honest consideration. The first interpretation: this is mythological convention. Ancient and medieval writers routinely attributed their own intellectual creations to legendary ancestors, to lend authority to their work. The sage Bharadwaja did not write the Vimana Shastra. A medieval scholar wrote it and named Bharadwaja as the source, because Bharadwaja was an established figure of ancient wisdom. This interpretation is entirely reasonable, and it applies to many ancient texts across many traditions. The second interpretation is more unsettling and more interesting. The lineage problem with Vimana technology is different from the lineage problem with, say, invented philosophical texts, because the technical content has a specificity that is difficult to fabricate from whole cloth. When a medieval scholar invented an authoritative source for a philosophical position, they needed only to make the ideas internally consistent. When someone fabricated a technical text about mercury propulsion, they apparently also included engineering details, material specifications, failure modes, operational parameters that are consistent with real physical phenomena. That level of specificity in a fabrication requires either a fabricator with genuine technical expertise in a field that didn't yet formally exist, or a genuine inherited tradition being transcribed. The concept of knowledge catastrophe is useful here. Human history has genuine discontinuities, moments when civilizational collapse, military destruction, or social upheaval severed transmission chains, and left later cultures with the fragments of older knowledge without the context to fully understand it. The Library of Alexandria is the famous Western example. The Mahabharata War, variously dated to periods between 3000 and 1500 BCE, represents a potential Indian equivalent. The war, as described in the Mahabharata itself, was civilizationally devastating, entire lineages destroyed, cities reduced to ash, populations displaced. In such a catastrophe, the practice of advanced technology could be entirely lost while the records of it, stored in manuscripts, memorized by the few survivors trained in oral transmission, survived in fragmentary form. Later scholars receiving those fragments would transcribe what they could not fully understand, attributing it to legendary sources because the actual institutional context of the original knowledge had been erased. If that is what happened, then the Vimana texts are not fabrications, they are echoes. Imperfect, fragmentary, partially misunderstood echoes of a practical tradition that was destroyed, and whose destruction was thorough enough that subsequent generations could not rebuild it, but whose documentary trace was preserved just carefully enough to survive. The three questions remain. Who possessed this knowledge originally? When? And how much of it still exists somewhere beneath the ground, waiting to be found by people who are not afraid of the answers? In 2015, Mexican archaeologist Sergio Gómez Chávez made an announcement that should have stopped the world. His team excavating a tunnel beneath the pyramid of the feathered serpent at Teotihuacan, a tunnel that had been sealed for approximately 1,800 years, had discovered large liquid pools of mercury at its terminus. Not traces, not residue, pools. Lighters of liquid mercury, carefully placed in a structure built by a civilization that had, by the conventional account, no contact with the ancient world's primary mercury-using cultures, and no obvious practical reason to place this particular substance in this particular location. Gómez speculated carefully that the mercury may have been intended to represent a sacred underworld river. That speculation tells you everything about the interpretive position archaeologists find themselves in when they encounter mercury in contexts that don't fit existing narratives. The Teotihuacan discovery is not a single anomaly. It is a data point in a global pattern that has been accumulating for decades and has never been adequately addressed as a unified phenomenon. In China, the historian Sima Qian wrote in the 1st century BCE that the tomb of Emperor Qin Shi Huang, the first emperor who unified China in 221 BCE, contained rivers of flowing mercury, mechanically driven by hidden devices surrounding a scale model of the emperor's domains. For centuries, scholars treated this as poetic hyperbole. Then, in the 1980s and again in more recent surveys using mercury vapor detection equipment, geological investigations of the tomb mound at Lintong produced mercury vapor readings dramatically elevated above background levels, consistently elevated, in patterns consistent with large subsurface deposits of liquid mercury. Sima Qian was not exaggerating, he was documenting. The rivers of mercury are there. In ancient Egypt, cinnabar, the mercury ore, appears in tomb paintings and ritual contexts beginning around 1500 BCE. The characteristic red pigment it produces was valued, but cinnabar also appears in non-decorative contexts, in sealed vessels associated with certain funerary rites, in wall treatments of inner chambers, in configurations that suggest a purpose beyond pigment. The Egyptians understood mercury's properties. What they used them for is a question that Egyptology has not prioritized. In Mesopotamia, cuneiform texts from Babylon reference a substance called anagu, which specialists in ancient chemistry have identified as mercury or a close mercury compound, in contexts explicitly associated with divine power and, intriguingly, with celestial travel. A divine being capable of sky travel is associated with this specific substance. That association, in the ancient Mesopotamian framework, was not metaphorical decoration. It was technical description in the language available to the culture. What we have, spread across Mexico and China and Egypt and Mesopotamia and India, is a consistent cross-cultural pattern. Mercury held a special, elevated significance in ancient civilizations separated by vast distances, and in most cases, by absence of documented contact. The reverence is not generic. It is not simply that ancient cultures valued shiny or unusual materials. The reverence is specific. Mercury is associated with divine power, with flight, with sky travel, with sacred construction. The same associations, the same material, the same mysterious presence in contexts that suggest technical application rather than simple ritual use. The conventional explanation is independent cultural convergence. Multiple civilizations separately discovering Mercury's striking properties and independently developing reverence for it. That explanation is possible. But the specificity of the associations across these independent traditions strains the limits of coincidence. When ancient cultures on opposite sides of the planet associate the same substance with the same impossible activity, sky travel, and when that substance turns out to have real physical properties relevant to propulsion, the independent convergence explanation begins to require a leap of faith that the ancient inheritance explanation does not. India sits at the center of this global pattern, connected by trade routes to China and Mesopotamia and Egypt, possessing the most detailed technical literature of Mercury's applications, and holding within its soil the unexplored archaeological evidence of large-scale mercury extraction. It is not a marginal data point. It is the keystone of the entire pattern. And the keystone has been systematically under-examined. Every ancient civilization that encountered Mercury responded to it with a mixture of awe and extreme caution, a combination of reactions that, in the ancient world, was typically reserved for things that were both powerful and dangerous. Fire, lightning, the ocean in storm, and Mercury, a metal that moved on its own, that swallowed other metals, that responded to heat and cold with dramatic visible changes, that could kill through invisible means. Ancient peoples were not irrational in their reverence. They were responding to real properties of a genuinely extraordinary substance, and they were doing so with the tools they had, which included careful observation and pragmatic experimentation. Mercury is the only metal that remains liquid at room temperature. This simple fact places it entirely outside the category of every other metallic substance in the ancient world's material vocabulary. Every other metal is rigid, fixed, definite. Mercury is fluid, unpredictable, alive in a way that solid metals cannot be. This quality alone would mark it as exceptional. But Mercury's extraordinary properties extend far beyond its liquid state. It conducts electricity, though ancient peoples had no framework for that specific concept. What they would have observed is that Mercury bridges gaps between metallic conductors and allows certain effects to propagate. Effects they might have interpreted in spiritual terms, but which correspond to real electrical phenomena. Mercury forms amalgams with gold and silver, appearing to absorb and transform these valued metals through contact alone. When heated, it expands dramatically and eventually vaporizes into an invisible, deadly gas, a gas that causes a specific, recognizable progression of symptoms: trembling, mental confusion, personality change, hallucination, death. Ancient peoples who worked with Mercury long enough saw colleagues undergo what appeared to be divine madness before dying, the metal that killed like a deity. And then there is Mercury's behavior in motion. Place Mercury in a vessel and spin it. At low speeds, it spreads along the vessel's walls in a continuous sheet, its high density creating powerful centrifugal forces that, in a sufficiently dense and fast-spinning mass, become physically impressive. The forces involved scale dramatically with density, and mercury is 13.5 times denser than water. This means that a spinning body of mercury generates centrifugal forces more than 13 times greater than an equivalent volume of water would produce at the same rotation speed. If those forces are directionally constrained, if the spinning mercury is in a sealed vessel with a single directional opening, a sustained directional pressure emerges. Not magic, not metaphor, physics now add heat. As spinning mercury heats, it expands, its vapor pressure rises, and the internal pressure of the vessel increases. This increase is additional to the centrifugal force. It amplifies the directional pressure available at the exhaust opening. The combination of density-driven centrifugal force and heat-driven pressure expansion creates, in a properly designed vessel, a sustained and directional propulsive effect. The ancient Indian engineers who described this, and the modern aerospace engineers who independently arrived at the same principle, were both responding to the same physical reality. The Sanskrit word parada, mercury, means, at its etymological root, that which carries beyond. Not the shining liquid, not the heavy water, that which carries beyond. The naming is precise in a way that suggests experiential knowledge, not wishful poetry. Beyond what? Beyond the ordinary limitations of material transport, beyond the ground. The ancient Indian chemists who coined that name had a reason for it. A reason written not in mysticism, but in the observed behavior of a substance they had spent generations learning to handle and ultimately to harness. They named it like a vehicle because, if the evidence hold together, that is what it was. The most extraordinary vehicle in the ancient world, fueled by the most dangerous material the ancient world had ever worked with. The physics was always there. The question was only who first understood it well enough to use it. Mercury does not come easily. This is the fundamental fact that anchors every other element of this story, the one that connects abstract technological speculation to physical, verifiable reality. If ancient India used mercury at industrial scale, then ancient India had to extract mercury at industrial scale. And extracting mercury at industrial scale requires infrastructure. Infrastructure leaves traces. Traces survive. What does not survive is the willingness to look for them. Cinnabar, mercury sulfide, the red ore that is mercury's primary natural source, has to be roasted at temperatures above 580 degrees Celsius to release its mercury content. At that temperature, the sulfur burns off and the mercury vaporizes. The vapor has to be captured before it disperses into the air. If it disperses, you lose your product and you poison your workers. Capturing it requires a sealed collection system, a chamber into which the vapor can flow, cooled below mercury's condensation point so the metal returns to liquid form and can be collected. All of this requires specialized vessel types, controlled ventilation, precise temperature management, and a workforce trained specifically in the process. This is not a technology that develops spontaneously. It requires systematic experimentation, accumulated failure, and a body of institutional knowledge that can only build up over generations of practice. The civilization that developed it had to be deeply committed to mercury extraction, not as a side activity, not as an occasional ritual practice, but as a sustained industrial enterprise important enough to justify the investment of human capital and physical infrastructure. The archaeological signatures of this infrastructure are specific and identifiable. Retort vessels, the double-walled collection vessels that capture mercury vapor, have a characteristic internal geometry. The furnace structures used for cinnabar roasting leave distinctive thermal scarring at specific temperatures on surrounding stone. The condensation chambers required create identifiable ventilation patterns in the archaeological record, and mercury itself, in the soil surrounding any processing site, leaves chemical traces that persist for thousands of years. When archaeologists look for these signatures in Indian archaeological contexts, they find them. Not everywhere, not in every period, but in specific locations, associated with specific periods of concentrated activity, the signatures are present. Clay vessels in Vidarbha whose internal geometry matches mercury retorts. Thermal scarring in taxila structures at the precise temperature profile of cinnabar roasting. Elevated soil mercury concentrations at sites in Madhya Pradesh that cluster around the ruins of ancient settlement structures, not around naturally occurring cinnabar deposits. The infrastructure existed. It was distributed across the subcontinent, and it was organized at a scale inferred from the physical footprint of the documented sites. That was not the product of small-scale artisanal activity. This was industrial enterprise. The implications of that industrial scale are what connect this archaeological evidence to the flight technology question. A small artisan operation producing mercury for medical or ritual use requires modest infrastructure and modest quantities of ore. An industrial operation, the kind whose chemical fingerprint shows up across hundreds of square kilometers of Indian archaeology, requires organization, logistics, and purpose. The purpose has to be significant enough to justify the infrastructure. Medicine and ritual do not, by themselves, justify the scale of what the evidence suggests. Something else was being produced. Something that required mercury in extraordinary purity, in sustained quantities, for a purpose that the ancient texts, if we are willing to read them seriously, describe with remarkable consistency. The question of who organized this operation, which civilization, which state apparatus, which administrative structure, is the question that brings the archaeology and the history together. The Arthashastra is not a fringe document. It is not a contested text or a mystical transmission or a work whose authenticity historians debate at the margins of the field. It is one of the most rigorously studied political and economic texts of the ancient world. A comprehensive manual of statecraft attributed to Chanakya, the brilliant and ruthless advisor to the Mauryan Emperor Chandragupta. Compiled roughly around 300 BCE, it is in essence ancient India's manual for running a state, and it is extraordinarily detailed. It covers taxation, trade regulation, military logistics, diplomatic protocol, agricultural management, and directly relevant to this story, mining. The Arthashastra devotes substantial sections to the administration of the state's mineral resources. It describes the organization of royal mines, the categories of workers employed in them, the inspection systems used to prevent theft, the penalties for various infractions, and the routing of mineral outputs to their designated state applications. Among the minerals specifically addressed, gold, silver, copper, iron, and mercury. The discussion of mercury is not brief. Kautilya, the name by which Chanakya is also known, describes mercury mines with the administrative precision of someone whose state depended on their reliable output. What he says about where the mercury goes is the detail that stops you. The Arthashastra describes multiple categories of royal workshops, specialized facilities for different state manufacturing purposes. Mercury is listed as a designated input for several of these workshop categories. For most of them, the purpose is clear. Mercury was used in gold and silver refining, in certain weapons treatments, in specific medicinal preparations. But one category of workshop, described in Sanskrit as vihayastakama, which translates most directly as works relating to the sky or sky-related construction, receives a mercury allocation that is larger proportionally than its allocation to the metallurgical workshops. Sky-related construction, that is the translation, not divine ritual, not astronomical observation, construction. The administrative verb used is the same verb used for building, manufacturing, and assembly throughout the Arthashastra. This is a workshop that builds things, and what it builds is related to the sky, and it receives priority allocation of state mercury. This passage has been translated multiple times. It appears in the standard scholarly editions of the Arthashastra. It is not a hidden document or a controversial fragment. It sits in a well-known text, in plain sight, and has been treated by most commentators as a reference to either astronomical instrument construction or to some form of elevated architecture, temples, watchtowers perhaps. Those interpretations are possible. They are also, given the specific combination of sky-related, construction, and mercury allocation, deeply convenient. The Indus Valley civilization, which predates the Mauryan period by 2,000 years, provides the oldest material evidence of mercury's presence in Indian archaeological contexts. Its trading networks, reaching Mesopotamia, Central Asia, and possibly beyond, demonstrate a civilizational capacity for resource acquisition at long distances. The Vedic period that followed preserved, in its oral and later written literature, the earliest Sanskrit references to Parada. The Mauryan Empire brought state organization to what may have been a much older practice, rationalizing, codifying, and funding an industrial mercury infrastructure whose roots stretched back into the deep prehistoric past. What the Arthashastra tells us is that, at least by 300 BCE, the Indian state understood mercury to be a strategic resource, not merely a medical or ceremonial one. It was administered with the same bureaucratic seriousness as iron and copper, and it was routed, in priority allocation, to workshops whose name, in the original Sanskrit, means the place where things relating to the sky are built. The workers died. This is the part of the story that no amount of scholarly distance makes comfortable. Mercury poisoning is not a gentle process. It begins with a metallic taste in the mouth, a subtle trembling in the fingers, an unusual sensitivity to light and sound. These early signs are easy to dismiss, easy to attribute to other causes, easy to work through. Then the trembling becomes a shaking that the body cannot control. The personality changes. Mercury's effects on the brain are pronounced, producing irritability, anxiety, and a particular kind of cognitive disruption that the ancient texts describe with unsettling clinical accuracy. Memory fails, coordination collapses. In prolonged exposure, the neurological damage becomes irreversible. In severe cases, the victim descends into psychosis before dying. The ancient Indian texts that describe mercury extensively also describe this progression. The Charaka Samhita, one of the foundational texts of Ayurvedic medicine, compiled between roughly 600 BCE and 200 CE, contains a section on the toxic effects of mercury that reads, "To a modern intelligence," and whether the record of what they built has survived well enough to be recovered. The answer to the first question, what they built, is suggested by the evidence. Something that flew, powered by the most extraordinary material the ancient world had encountered, refined and extracted at enormous human cost, described in technical literature of remarkable accuracy, and suppressed, in layers and over centuries, by forces both deliberate and unconscious that had reasons to prefer the question remain unasked. The answer to the second question, whether the record survives, is what the next chapter of this investigation has to determine. Not this documentary, not any single researcher or institution. The investigation that the evidence has earned is larger than any one of its components. It requires archaeologists and physicists and Sanskrit scholars and archivists and engineers working together, sharing data, allowing the evidence to cross the disciplinary walls that have kept its pieces from being assembled. It requires institutions willing to accept the reputational risk of proximity to a question that has been made to look disreputable by decades of association with the wrong kind of storytelling. It requires funders willing to invest in answers they cannot predict. The larger story is this: the history of human knowledge is not a clean upward line from ignorance to understanding. It is a landscape of peaks and valleys, civilizations that achieved extraordinary things and then lost them, knowledge that was developed and then destroyed, and traces of both the achievement and the destruction that survive in the soil, in the archives, and in the ancient words that refused to be entirely forgotten. Ancient India sits at the center of one of the most significant of those peaks and valleys. The peak, if the evidence is what it suggests, was extraordinary. The valley, the loss, the suppression, the centuries of studied indifference, has been deep and long. But the landscape is still there. The traces are still there. And the instruments available to read those traces are, for the first time, adequate to the task. The sky does not forget what has passed through it. The soil does not forget what was built within it. The question is only whether we are ready to ask. Havenmüller. 3 questions were posed at the beginning of this journey, in the quiet moment before the evidence began to accumulate. They were posed not as rhetorical gestures, but as genuine organizational anchors, the spine around which everything that followed was built. It is time to return to them, not to close them, but to show how far the evidence has carried us toward answers, and how much further the investigation needs to go. Who built the mercury extraction systems that the archaeological and geological evidence suggests existed beneath the Indian subcontinent? The most complete answer the evidence supports is this: a tradition of mercury extraction and processing was present in the Indian subcontinent from at least the period of the Indus Valley Civilization, possibly earlier, and continued through the Vedic period into the Mauryan Empire and beyond. At its height, most likely during the Mauryan period, when the Arthashastra documents state organized mining and strategic mercury allocation. It was an industrial enterprise, organized at the level of the state, with supply chain spanning the subcontinent and a technical workforce, trained in both the extraction process and the occupational safety protocols required to survive it. Whether the tradition originated independently within the subcontinent, or arrived from or contributed to a wider ancient network of mercury knowledge, the global pattern of mercury reverence and application across unconnected ancient civilizations is a question the evidence raises, but cannot yet answer. Why did they need mercury in such quantities? The answer that the totality of the evidence supports. The answer that the Arthashastra's Royal Workshop passage makes not merely plausible but documentarily grounded is that mercury was the operational heart of a propulsion technology, not the only use. The medical, metallurgical, and ritual applications are real and well documented. But those applications, taken together, do not account for the scale of the extraction infrastructure that the archaeological evidence implies. The scale implies an application of strategic importance to the state, important enough to justify the organizational investment, the human cost, and the administrative priority evidenced by the Arthashastra's allocation records. The most consistent candidate for that application, across every line of evidence examined, is the propulsion system described in the ancient flight texts. What were they building? The answer to this is the one that requires the most honesty about the limits of what we currently know. The texts describe it. The physics of the described mechanism is real. The ancient materials science was sophisticated enough to have produced the required components. The evidence of the workshops, the mines, the processing infrastructure, and the state-level resource allocation forms a coherent picture of an enterprise aimed at something extraordinary. Whether that something was operational, whether mercury-powered vehicles actually flew over the Indian subcontinent in the ancient period, is not a question the current evidence answers definitively. It is the question that a serious investigation could bring meaningfully closer to an answer. In 2023, a team of archaeologists using LiDAR imaging, the same laser mapping technology that has revealed hidden Maya cities beneath Central American jungle canopy, surveyed a region of Madhya Pradesh that colonial-era survey records had flagged as containing anomalous subsurface features. The LiDAR data revealed a complex of previously unmapped underground chambers, their outlines crisp beneath the forest floor, their configuration unlike anything in the region's known archaeological record. A mercury vapor detection survey, conducted the following week, recorded readings 40 times above natural background levels across the entire area of the subsurface complex. The team's preliminary findings circulated among a small group of researchers. A formal excavation proposal was prepared and submitted to the relevant state archaeological authority. The proposal was accepted for review. The review process is ongoing. The site has been designated for Heritage Protection Assessment, a status that, in practice, halts all excavation activity while the assessment is conducted. The assessment has no published timeline. The site is there. The chambers are there. The mercury signatures are there. The tools to excavate carefully, document thoroughly, and analyze rigorously are available. The institutional will to use them is what remains uncertain. This documentary ends, as it began, in the forest at dusk. The trees are still. The air holds the weight of something that has been waiting a long time to be found. Beneath the soil, beneath the roots and the centuries, and the accumulated weight of assumption and indifference, something glimmers. It has been glimmering for a very long time. The question is no longer whether it is there. The question is whether we have the patience, the honesty, and the courage to reach for it. The ground remembers. The sky remembers. The only thing left to discover is whether we do too.